All right, we know about the physical properties of minerals and the definition of minerals. Now let's talk about how we classify them. We're going to classify them today with their chemical composition. And there are two main groups, either the silicates or the non-silicates. And it's based on the anions. We're going to look at the anion or the anion group. And the last line there, the most important mineral class is the silicates, the SiO4s, and then there's all the other ones. So silicates have that negative anion group, SiO4, and then some cation attached to it. The same thing for the carbonates and the sulfides and the oxides and the halides. They have some anion with a cation attached to it. So they're classified by the anion. The biggest, most important group are the silicates, and then there's a bunch of other smaller groups. So let's look at the smaller groups first. Then we'll go back to that important group, the silicates. Nope, we're going to start with silicates. The silicates are the group is classified as the rock-forming minerals, and they are the ones that make up the almost all of the Earth's crust and mantle are these rock-forming minerals. They are the most common minerals. They're the most common because the silica and the oxygen are the most common in the crust. The main example is quartz. So this is a quartz crystal here. It's a silicate mineral. The oxides have O2 is their anion, and then different cations, iron or titanium. Here's two examples, magnetite and hematite. Similar chemical formulas, but they're very different. And titanium to make the mineral rutile. Here's an example of a banded iron formation. That's what iron usually looks like in nature. It's combined with oxygen, kind of rusty looking like hematite. Pyrite is in the sulfide group. So sulfur is the anion, then we can add iron or lead or zinc and form different minerals. So the sulfides have just sulfur as the anion. The sulfates have sulfur combined with oxygen as an anion group, and then can have different cations in the front. So examples here would be gypsum or anhydrite. These both evaporate, precipitate as seawater evaporates. The next one are the halides. In this case, it's kind of a simple formula, just a cation and an anion. And here the halides have either chloride or fluorine as their anion. Carbonates, we talk about carbonates a lot because this is what makes up calcite, which makes up the rock type limestone, and caves are made out of, are forming in dissolved limestone. So we talk about calcite a lot. So calcite is the main carbonate. It's calcium carbonate. Then there's also dolomite, where some of that calcium is replaced by magnesium. There are some minerals in this group here especially that are really simple. They have just one element, and these are the native minerals. So whether it's gold or silver or copper, there's just one element. It's not combined with a cation and an anion, just one element. Those are the natives. All right. So looking at the Earth's crust, there are only about 50 abundant minerals of the 4,000 minerals that are found in the Earth, that we found on Earth, making up Earth. There's only 50 main ones. And if we look at the chemical composition of the Earth's crust, it's mostly made out of oxygen and silicon and aluminum. So if we take oxygen, silicon, and aluminum and put them together in a mineral, it makes the mineral feldspar. So that is the most common mineral in the Earth's crust is feldspar, and it's a silicate. And so Si and O together make up quartz, and most of those abundant 50 minerals are silicates. So here's the silicates. They're known as the rock-forming minerals. There's an ant on my table. The rock-forming minerals, and they dominate the crust and the mantle. And it's made up of that silicon and oxygen. We'll go back and slide the silicon. Whoa, there's my head again. The silicon and oxygen, and then adding in other atoms, mostly cations. Silicates have a structure to them. So we're going to talk a little for a couple slides about silicate structure. The base of the silicate structure is the silicate tetrahedra. And you see a lot of triangles here. You have a silicon in the middle and 4 oxygens around that silicon. So here are different ways to show that model of the silicate tetrahedron. So all of the silicate minerals have this as their base, the silicate tetrahedron, and then you can add in, with the quartz doesn't have any other atoms, but all the other silicates are going to have cations attached to that silicate anion, the tetrahedra that acts as the anion. Okay, now all those tetrahedra fit together in different ways. We call those the different silicate structures. So let's look at those groups, and it's all about the ratio of silicon to oxygen and how many corners are being shared. And once you can figure out that ratio of silicons and oxygens and what's being shared with all the tetrahedra, it can tell you a lot about melting temperatures, what cations can fit in there, and susceptibility to chemical weathering. That's beyond the scope of this course to get to that detail, but we'll look at some of those structures. Okay, so the first one, the independent tetrahedra, where each tetrahedra is not touching another tetrahedra, and they are separated from each other by cations. So the cations are between those anion tetrahedra. Examples of that are olivine and garnet. So there's an olivine is olive green, there's a piece of olivine there. This example over here is the single chains. And in the single chain, you literally just have the one corner of the tetrahedra touching another one. You make just a long chain of tetrahedra. Then those chains are hooked to each other by cations. An example here is pyroxene. Now, if we take those chains and we hook 2 chains together, it's a double chain. Amphibole is an example of that. And now you've got all the corners being bonded within those chains. Then on the outside of that chain, you would have other cations hooking the chains together. A sheet silicate, now we're going to have all of the tetrahedra in a layer all attached. So muscovite or biotite in this example here is a sheet silicate. You have a sheet of tetrahedra, and between the sheets are those weak van der Waals bonds. That's how you have that one plane of cleavage. The micas are sheet silicates, all the tetrahedra fitting in a sheet. The framework silicates, you have all the tetrahedra and all the corners all being bonded. So all of the silicates are touching other silicates. And the example of that would be those feldspars that are the most common mineral in the Earth's crust, and then also quartz is a silicate framework structure, silicates. Gems. All right, so we like shiny things. Gems are minerals that are rare. They have some special value. They're beautiful. They're shiny. They're clear. They have sparkly in the sun. And so we can find those precious resources in the correct geologic setting. Then we can take that gem, we can cut it. So the faces of these gems, they've cut them with a special lapidary, I forget what it's called, the stuff that cut gems. The example of that tourmaline quartz, watermelon tourmaline, where it has the red with the green around it, watermelon tourmaline, that is just broken, it's not cut. It could be cut that way. The precious stones would be like diamonds, rubies, sapphires. Remember, ruby and sapphires are just the mineral corundum. There's some that are less rare, tourmaline, topaz, aquamarine, garnet, maybe less expensive. And there's other gems as well, but there's a whole trade for gems, and people collect them, and queens wear them. Where do diamonds come from? So that leads us to diamonds. If you've never seen a rough diamond, how you would find it laying in a creek, They look like this, just blobs. They can have crystal faces, like a double diamond crystal faces, but they are not that special to look at, to just see. To get the real sparkle from them, you have to know how to cut them. And they form in what's called kimberlite. So this is a chunk of kimberlite right here. Kimberlite forms deep in the earth, maybe down in the upper mantle. And so they're deep in the earth. They come about 150 kilometers deep. They come up to the earth's surface in what's called a kimberlite pipe, almost like an eruption of material. And it's a pipe shaped like a column of material. And so mining for it looks like this, where you just go down that kimberlite pipe, and along the way you find diamonds as you go. So that's how diamonds are found.